Hello Beyond the Five students. My name is Angel Jimenez, and welcome to Unit 5.3, Concentration Changes Over Time. By the end of today's lecture, you should be able to explain the form and function of an integrated rate law, perform integrated rate law calculations for the zero, first, and second order reactions, define half-life and carry out the related calculations, and identify the order of a reaction from concentration or time data. Without further ado, let's get straight into today's lecture. So what is an integrated rate law? Well, an integrated rate law relates the concentrations of a particular reaction to time. Now, here is the first order integrated law equation. Now, don't freak out. We're going to walk through this together, and we're going to break it down bit by bit so we can make this as less complicated as possible. The first thing you're going to notice is the ln, and that just stands for the natural logarithm of. It's a calculus calculation that you can find easily on your calculator. If you have a TI-84 calculator, it's literally a button that's labeled ln, and you use that whenever you're trying to find out, whenever you're trying to use this equation to find out a calculation. The concentration of A with the 0 being divided by the concentration of by the concentration of A is the initial concentration over the concentration at a specific point in time of a reactant or product. So the 0 simply means the initial concentration, and then sometimes the A on the bottom is given a little t, and that simply just means the concentration at a specific point in time. Moving on. K is going to be your first order rate constant, and this will change depending on what order you're in. So if you have a K in the second order, then it is your second order rate constant, and a K in the 0 order is the 0 order rate constant. And lastly, T, and T simply stands for time, and that's the specific time that concentration that I was talking about earlier belongs to. So there is a certain way of determining if a reactant is in the first order, and that's by graphing it out. So whenever you graph a set of data using this equation on the right, which is the natural logarithm of the concentration of A, and you graph that versus T on the x-axis, then if you get a straight linear line, that reactant is guaranteed to be in the first order. So let's do this out real quick. We have a chart of data right here, and I'm going to do some calculations real quick. I'm going to take the natural logarithm of, or the ln of A, the concentration of A at 0 hours, which is 1, and I'm going to get an answer of 0. So my first dot is going to be 0, 0. Next, I'm going to do the ln of 0.5 at 6 hours. So ln of 0.5 is a little bit below 0. It's 0.693, negative 0.693. And so we're going to put that in there. Now I'm going to do the ln of 0.250. And I'm just going to follow this for the rest of the hours. So I'm going to get an answer of a little bit greater than negative 1. Or a little bit smaller than negative 1, I should say. If I do the ln of 0.125, I get an answer of a little bit smaller than negative 2. Then if I do the ln of 0.0625, I get an ln of doop. And now, if we do try to draw a line along these set of points, you can see that it fits in a linear line. It does work as a linear line, meaning that we can accurately predict that H2O2 is a reactant in the first order. Okay, now we have the second order integrated law equation, and that's going to be 1 over the concentration of A at a specific point in time minus 1 over the initial concentration of A is equal to K, which is the second order rate constant, remember, because we're in the second order, times T, which is time. Now, there is a way to determine if a reactant is in the second order, and I'm going to show you a glimpse of it, and it's just by using one simple equation, and that equation is going to be 1 over the concentration of A at a specific point in time versus time. I don't feel like we need to go over how to do this, because it is just graphing points, but you would just need to plug in any data you're given from a table into that equation, which is 1 divided by the concentration of A. So you need to plug in the concentration of A, and then just graph it at a specific time. And if it forms once again, a linear line, Even you might be thinking, oh, it's a second order reaction, or it's going to form like an exponential. No, if it forms a linear line, then it is second order. If it forms an exponential line, it is not. And that also goes with the first or zero order. If you're testing out whether it's a first or second order reaction, and you get a set of points that form an exponential line, then it is not that kind of a reaction. And you need to try a different equation. Next, we're going to move on to the zero order integrated law equation, which is just the initial concentration minus the specific concentration at a point in time times K, which is the zero order rate constant now, and T, which is once again time. And this time, to find out whether a reactant is in zero order, all you need to do is take the concentration of that reactant and graph it along T. Pretty simple enough. Now we're going to move on into something else, and this is called a half-life. So what is a half-life? Well, a half-life is a period of time in which the original concentration of a reactant is reduced to 1/2 of its former value. There are 3 half-life equations, one for each main order. So the zero order half-life equation is the initial concentration of the reactant divided by 2K, K being the zero order rate constant. The first order equation, half-life equation, is going to be 0.693, which is ln times 1, which is ln of 1, the natural logarithm of 1, divided by K, which is the first order rate constant. And the half-life equation for the second order is going to be 1 divided by K, which is the second order rate constant, times the initial concentration of the reactant. Okay, and that's going to be it for today's lecture. I do hope that it helped you out. Please don't hesitate to contact me on Discord or through email if you have any questions. And also, I want to make a huge note right here that the equations shown in today's video can be manipulated and changed around. I'm using the equations that I got from my classes. They might be different from the ones you've been given. I do have alternate equations that might look a bit similar to the equations you have. So please don't think that your equations are wrong. They might just be in a different They might just be different from what I have, and that's perfectly fine. In math, you can change around equations and still get the same answer. It's why math is so beautiful. So as long as you think that your equation is right, then it most likely is. I would verify it online. You can also verify it with me. Contact me through Discord or email, like I just said, and I would be more than happy to help you out. Anyways, I hope you did get something out from this lecture, and I wish you all the best of luck in your studies.